Cameron Fahrig. I'm the leader for Group 2. I'm going to be discussing next week's experiment, which is an experiment 2, the Clapeyron experiment. So for our introduction, the Clapeyron equation relates the saturation pressure, saturation temperature, the change in enthalpy due to the phase change, and the specific values of two phases. And we're going to, in this particular experiment, we're going to use it to determine the changes in enthalpy, which otherwise we wouldn't be able to directly measure. So we need this equation to be able to find that. So the latent heat of vaporization, or the enthalpy of vaporization, is the enthalpy change that's required to transform a given quantity of any substance from a liquid to a gas at a given pressure. And we utilize the Clapeyron equation in order to determine the enthalpy of vaporization over a range of temperatures and pressures. And we're going to verify those values that we calculate from our experiment and using the steam table values. So the theory is that you use the Clapeyron equation with the saturation, pressure, and temperature data that we get from our experiment in order to find the enthalpy of vaporization. And right here we have the Clapeyron equation. It's the change in the pressure, saturated pressure over the change in saturated temperature. It's equal to the specific entropy over the specific value, or it's also equal to the enthalpy of vaporization over saturated temperature times the specific value. But since we don't know the specific value, whenever we get our data in our tables, we're going to use it, we're going to approximate the specific value using the ideal gas equation of state. That would give us all this kind of stuff. This is the change in, it'll be equal from the change in saturation pressure over the change in saturation temperature equal to the enthalpy of vaporization times the pressure saturation over the saturation temperature squared times the gas constant of steam. So for our procedure, we're going to be heating water in a flask on a hot plate under a vacuum, which is going to be near zero pressure. We're going to get that vacuum using a centrifugal pump, and then we're going to begin logging our data whenever we get the water to boiling with our PDAC program, which is our data acquisition program, so that we can tabulate our values for the pressure, saturation pressure, and saturation temperature as the water in the flask turns to vapor. We're going to slowly increase the pressure while we keep logging our data while it's boiling, and then we're going to continually check those values. And once we get our pressure to near atmospheric pressure, we're going to stop logging data and use that as our standard point for our boiling point of water. And then we're going to turn off the hot plate and then allow the beaker to cool off. So this is our apparatus that's provided for you in the lab manual. This is going to be our hot plate. Well, that's the flask. This is going to be our hot plate. Number 3 is the thermocouple that's going to be used to check the values for the saturation temperature. We have our pressure transducer right here, our pressure gauge, which will get us our values for the saturation pressure, which we get through our data acquisition program right here. The vapor will flow into these pipes into the reservoir. This is our air bleed, so that we make sure that we don't have any pressure buildup once we start increasing our pressure. This is our vacuum release valve, so that we can control our vacuum from our centrifugal pump. And with all this, we're going to be able to find our values for the saturation temperature, saturation pressure. These are some sample values from the steam tables to show you kind of what our data should look like. We're going to have the increase in temperature as we heat up our water in our flask, and that's going to give us an increase in pressure as they both increase. In order to use the Clapeyron equation, we're going to have to use the ideal gas approximation, and then we're going to integrate it and use it for a range of saturation pressures and saturation temperatures, and that's going to help us find our enthalpy of vaporization. And from some values from the steam tables, I was able to demonstrate this using just arbitrary ranges of pressures and temperatures that I got from the tables. And using the Clapeyron equation, I calculated each of these enthalpy of range to give some sort of reference to as to like how accurate it will be, and each of these values is pretty close to what's given to us in the steam tables. And for our expected results, we're going to have, as the saturated vapor temperature rises, we're going to also have our saturated vapor pressure rise. The Clapeyron equation should provide a good enough approximation for our enthalpy values, and the latent heat of vaporization should decrease as our saturated vapor temperature and saturated vapor pressures rise. So, any questions?